Hey guys, special relativity topic 2, the speed of light, time dilation, and length contraction. Okay, so in a nutshell, what we're going to establish is what's called the principle of the constancy of the speed of light. And again, you guys read and fill in the details, but historically what happens is if you take the wave equation, which you see in 2.1, you actually get a speed for light, and this is in vacuum or free space. It actually is predicted from Maxwell's equations. It should be 1 over radical mu naught epsilon naught, right? And you put the values in there and you get 3 times 10 to the 8 meters per second, the value we've been using. But then the question comes up, well, that's the speed of light relative to who, right? Because take a look in this picture, right? Let's say it's the old S prime diagram we talked about in topic 1. Let's suppose you're standing on the sidewalk in frame S, right? And you shoot your laser pointer and you measure speed C. Your friend is in a car driving down Central Avenue at speed V in frame S. According to Newtonian relativity, right? That person should measure C minus V then, right? Or how do we even know that your frame S is where the speed of light is in fact C? Because it seems like it's relative, right? In fact, what frame S does light travel at C? Well, that is called the ether frame. So we don't believe in the ether anymore, although some people do on the internet, but physicists tend to not to. But at the time, people thought, look, light, just like any other wave, needs some medium, right, to support the wave. So for instance, sound wave needs air or a fluid or a solid, right, to travel. Or a wave on a string needs a string. So people postulated that there was this stuff called the ether. It was very strange stuff because we're not really aware of it other than, right, it supports the oscillations for light. But what people thought was, look, there has to be a special frame that's at rest with respect to this mysterious ether. That's called the ether frame, and that is the frame where light travels at C. So anybody who's moving through the ether, right, in other words, not in the ether frame, has to measure a different speed for the speed of light. So there was a famous experiment done, by Michelson and Morley, 1887, where Michelson actually built the Michelson interferometer that we talked about earlier in class. And they were looking for a fringe shift because you have 2 perpendicular arms to your interferometer. So as you rotate the interferometer, you should be changing the speed of light because, right, the relative direction of the light is going to be changing with respect to the ether. So they looked for this fringe shift. They did not see it. Long story made short, right? The conclusion is there is no ether. We don't have to worry about an ether frame. And in fact, all observers measure the speed of light to be the same thing in free space. Now, this is a very, very interesting principle. As far as we can tell, it's true. Einstein came up with it also. He claimed that he didn't know the results of the Michelson-Morley experiment at the time, but came up with this just thinking about things. But in any case, this appears to be true. And only light has this special property that all observers, no matter how fast they're moving relative to one another, always measure the speed of light to be the same. And again, we're talking in free space. All right, so it would be C. Okay, so in the picture then, right, if we go back and somebody fires a laser pointer in frame S at speed C, anybody moving relative to that person, for instance, somebody in frame S prime moving at speed V is also going to measure C. Again, only light has this property. If you take a regular particle made out of matter, no, there's not going to be a constancy of the speed of that object. So only energy particles, i.e. photons, have this special property. Okay, so again, just an example to emphasize that everybody measures C. There's Jack and Jill again. Okay, now, some of the consequences of that. The ones I want you guys to be responsible for, concentrate on, are time dilation and length contraction. So here's a way to derive what we call the principle of time dilation. You'll see in the next video, topic 3, there's a more formal way to derive this also. Okay, but here's a little thought experiment. Suppose Einstein loved thought experiments, and he liked to put people on trains, since trains were really popular at that time. So imagine, we're going to update this though and give the person in the train a laser pointer. So here's a person, let's call her Jill, right, in the car of the train, and she fires a laser pointer straight up, hits a mirror, comes straight down. And the distance the light travels to the mirror is d. Okay, so if I look in frame S prime, we'll call that the car's frame, the light, if you look in this little triangle right here, the light beam goes d straight up, hits the mirror, comes straight down d. So how far does the light travel? 2d. How long does it take? We're going to say it's delta t prime as measured by Jill. So right over here, you know that the distance d is c delta t prime over 2. Right? Because the total distance 2d is the speed times delta t prime. So we're going to say, right, that she measures the speed of light to be c. So there's that equation right there. Now, let's ask ourselves, what does Jack see the laser beam doing if Jack is right here, stationary with respect to the tracks? Well, in fact, because the train's moving to the right at speed v, he's going to see the laser beam do this slanted path, hit the mirror, then another slanted path down to here. So if we look at this triangle, here's the path that the light makes as seen by Jack. Okay, now, the time from here to here for the laser beam to travel that zigzag is going to be delta t on Jack's clock. All right, so I know that this distance right here is c times half of delta t, because again, Jack's also going to measure the speed of light to be c. And then this path right here is going to be another c times half of delta t. So all we're going to do now is use the Pythagorean theorem on this triangle. This horizontal distance is the speed of the train times half of delta t. So the Pythagorean theorem gives us this equation. We do a little bit of algebra. The Pythagorean theorem gives us the first equation. We're going to substitute this we get from Jill's clock, a little bit of algebra, and we're left with this result. Now, I want you guys to see, right, here's the big finale. Well, it's not the finale yet, but here's a big implication. Delta t is not the same as delta t prime. They do not measure the same time for the laser to hit the mirror and come back to the starting point. Okay, and you can see that the difference depends on the relative speed of the observer's v. All right, so let's write this the usual way you see time dilation. We're going to define two terms here that are very important. Proper time interval, that's the time between two events that occur at the same position. Two events occur at the same position. If I go back here, that's got to be delta t prime, because for Jill, the first event, the laser beam leaving, occurs right here at her hands. The second event, the laser beam arriving, also occurs at the same position right at her hands. Okay, so she measures a proper time interval. So in this equation, on sheet 4, delta t prime is a proper time interval. Now, a time interval between two events that don't occur at the same position, that occur at different positions, we call that a non-proper time interval. It's not the best term, because when you hear non-proper, you might think incorrect. That's not what that means. It means it's a correct time interval. It's just that the two events did not occur at the same position. So back here in our train experiment, that's got to be delta t measured by Jack, because he sees the light beam, right, leave right here, and then it arrives farther down the tracks right here. Okay, so I can rewrite this equation that we got on sheet 4 like this. And this is how you usually see the statement of time dilation. A non-proper time interval is this factor gamma times the proper time interval. And that factor gamma, the gamma factor, that's just shorthand for this term right here. This is a very important factor. It pops up again and again and again in special relativity, the gamma factor. It's just a pure number, it's unitless, and it's going to depend on the speed between the two frames or the observers. Okay? In fact, if there's no motion between the observers, v is 0, gamma is 1. That's the smallest it can be. And then there's no difference between the delta t's. And as v gets bigger and bigger, gamma gets bigger and bigger and bigger, right? In fact, as v approaches c, gamma approaches infinity. Another way to think about time dilation is that the shortest time interval between two events is measured by the observer who sees the two events occur at the same position. A non-proper time interval is always going to be longer than a proper time interval. All right, here's just a picture showing what the gamma factor looks like as a function of v over c. So here's the speed times c. So 1 means v equals c. And you can see that gamma is essentially 1 until you get to really fast speeds. In fact, and that's why in our everyday life, we never see relative speeds anywhere near c, so the gamma factor is 1, and we're not really aware of these weird special relativity effects. Okay, it's only when you have tiny particles moving extremely fast that you see this. Here's a chart just showing what typical gamma factors are. You can see right here, for the Earth orbiting the sun, right? That's pretty fast. That's over 67,000 miles per hour. And look at the gamma factor. It's still essentially 1. Okay, so again, gamma is only going to be significantly greater for high-speed particles. Here's another implication, length contraction. Let's suppose that Jack measures a length for a bridge, right? So here's Jack right here, stationary right here, measures the length of this bridge. We'll call that L. Jill is moving in her car across the bridge and measures a length, right, L prime. Okay, now, the key here is she's going to measure a time, delta t prime, to cross this bridge. But that is going to be a proper time interval, because think about it. She has a watch on her wrist. Right when she hits this point, right, she starts her watch. When she hits this point, she ends it. But those two events occur at the exact same position for Jill, right? Here and here, she's in her car, right? She hasn't moved, right? So as far as she's concerned, that point and that point occur at the same position in her frame of reference, right? Where her car is. Okay, so Jack's going to measure delta t for Jill to cross the bridge. Well, that's going to be a non-proper time interval. So what we can conclude is that the two lengths measured by these observers are going to be different. Now, again, we put this in terms of a non-proper length and a proper length. Okay, so what do we mean by a proper length? That just means the object is at rest. That rest length is called the proper length, L sub p. So in this picture, Jack's going to measure the proper length of the bridge because Jack is at rest with respect to the bridge. Anybody who measures the object and sees the object moving, like Jill, right? As far as Jill's concerned, the bridge is moving. That's going to be a non-proper length. So we can rewrite this equation right here on slide 8 as a non-proper length is the proper length over gamma. And because gamma is greater than or bigger than 1, a non-proper length is always shorter than the rest length or the proper length. So we call that length contraction. Another way to think about it, right? The longest an object's going to be measured is when it's at rest with respect to you. Okay. And this last slide talks about a nice little example, experimental example of actual time dilation and length contraction. This was done in the early 1960s by Frisch and Smith. What they were looking at is they were looking at muons that are produced in our atmosphere. Protons coming primarily from the sun collide with oxygen and nitrogen molecules, and they produce particles called pions. The pions then quickly decay into mu mesons or muons. Now the muons also will decay into electrons. So what they were looking at is they were looking at the number of muons, okay, before they decayed into electrons. And what they did is they went up on top of this mountain in New Hampshire and they measured the muon flux, or the number of muons, traveling at a specific speed, 0.995 c, That's a gamma factor of 10 then between them and the muons. And they measured how many muons were left at the base of the mountain. Okay? Now, it turns out if the mountain's 2,000 meters and they're moving at 0.995 the speed of light, it should take the muons 6.7 microseconds, right, to come down here. It's also true that if a muon's not moving very fast, it'll decay after 2.2 microseconds. So it seems like this is about 3 times that 2.2 microseconds, the transit time. You shouldn't have very many muons right here. But it turns out you do. You do not get nearly the reduction that's predicted. However, if you take special relativity into account, it works because the time of 2.2 microseconds is dilated by a factor of 10 for people, right, the scientists. So really the muons are living about 22 microseconds on our clock. So that's 6.7 microsecond, right, transit time. That should not be much of a reduction. This is an average lifetime of 22 microseconds. Another way of thinking about it is, in the muons world, the muons frame, that mountain distance height is contracted. It's contracted to 200 meters. So if the muon's only going to live on average 2.2 microseconds, that 200 meters only takes about 0.7 microseconds in the muon's frame. So a lot of them are going to survive to the base of the mountain, right? So these results that they measure are explained by special relativity. It was quite a triumph for the theory. Okay, that's it. I'm going to stop right here. I'll pick it up in video 3. Bye-bye.